So we're going to talk a little bit about polynomials here. We're going to go straight back to reviewing definitions, all the way up to a few new concepts on zeros of polynomials and some new vocabulary that pertain to zeros of polynomials. So we'll start out here with what a polynomial is. So recall that a polynomial function has the form a constant times x to a non-negative integer power plus another constant times x to another non-negative integer power, and so on down the line. So essentially what you have is constants multiplied by x to a power, constants multiplied by x to a power. So the terms in a polynomial are separated by addition or subtraction, that is by a plus or a minus. The degree of the polynomial function, in this case f of x, is the largest power that appears on any variable term. So in this particular case, the degree of this polynomial is 5 because the largest exponent that shows up on an x is 5. The 7 to the 6th power that appears here in the constant term doesn't count towards the degree because that exponent is on a constant and not on the variable. So the entire term where the degree comes from, that is the highest degree term, is called the leading term of this polynomial. And in particular, the number that's in front of that term, in this case a 3, is called the leading coefficient. These are all words that we're going to be using repeatedly throughout the next section, so make sure you remember the vocabulary. So it turns out that graphs of polynomial functions are what's called continuous, and essentially the idea there is there's no breaks or holes in the graph. Another way of thinking about continuity is that you can draw the graph without ever lifting up your pen or your pencil. There are some polynomials that get special names, and these names change by degree. So first of all, if you have a degree 0 polynomial, that polynomial is just called a constant. A degree 1 polynomial is called a linear polynomial because its graph is a line. We've seen quadratics already, that is degree 2 polynomials. The new ones here are cubics, that is degree 3 polynomials, and finally degree 4 polynomials are what's known as quartic polynomials. There's actually names for polynomials beyond degree 4, but we won't really need them in this class. So what I want to talk about next is something called the leading term test for a polynomial function. It tells you something about the graph. And what the leading term test pertains to is the entire leading term. In particular here, we're going to let a be the leading coefficient. Now, this leading term test has two different possibilities on the leading coefficient and two different possibilities on the degree. So we'll break that into a grid here. So across the top, each one of the columns represents a sign on the leading coefficient. In this case, if a is negative, a is less than 0. Or if a is positive, in which case a is greater than 0. The degree of the polynomial will also affect what we're interested in here. So in the rows in this chart, the first row is going to be an even degree. That is, the highest exponent is an even number. And the second row is going to be odd degree. That is, the highest exponent is an odd number. So in the case that you have an even degree polynomial, something like a square or a 4th power or 6th power, along with a negative leading coefficient, the ends of the graph, so to speak, sort of the edges way back to the left and way over to the right, sort of slope down like this. So one way you'll see people do this is the end behavior of this graph looks like this. It's a bit like the field goal thing in football, just turned upside down. So you'll notice here the dot, dot, dot that lies in the middle of these two arrows. That dot, dot, dot essentially says that we don't really know what the graph looks like in between the end behavior yet. But we can say what sort of the edges of the graph look like, so to speak. On the other hand, if you have an even degree polynomial and the leading coefficient is positive, the end behavior looks like the field goal sign. The basic idea here is it looks like the ends of a parabola. It's just whatever happens in between for right now is a bit of a mystery. On the other hand, if you have a negative leading coefficient and an odd degree polynomial, the end behavior looks as displayed. And finally, if you have a leading coefficient which is positive and an odd degree on that polynomial, the edges look like a bit like y equals x cubed. So it comes up, and then something happens in the middle with the graph, and then it exits the window in the top right corner. These symbols that we're using here denote what's called the end behavior of the graph, what happens at the edges. As time goes on in this chapter, we're going to fill in what happens in the middle. But for right now, we just know what's going to go on at the end. So let's apply this in an example. So in this example, we want to find the end behavior of two different functions. In part A, negative x to the 6th plus x to the 4th minus 4. And in part B, x to the 7th plus 2x plus 2. So we'll go ahead and do part A together, and then you can work on part B, and then you can come back and we'll take a look at the solution. So for part A, notice that the leading coefficient is -1 here. That negative that's out front of that x to the 6th term is the leading coefficient, which is -1. It's a negative number, it's less than 0. On the other hand, the degree is an even number. The degree is 6. In which case, if you look back on that last slide, if you back the video up a little bit, the end behavior sort of points down on the edges with some mystery stuff in between, denoted by that ... So at this point, go ahead and pause the video, take a shot at part B, and come back when you're done. So now that you've taken a shot at part B, we can look at the solution. The leading coefficient of this polynomial is just 1. Notice there's no number attached to the highest degree term, that is x to the 7th, and so the leading coefficient here is just the number 1. But that's a positive 1, and it's a positive number. The degree, on the other hand, is 7 because the largest power that shows up on any variable, in this case x, is the 7th power. So we put that all together and we find out that the end behavior sort of enters the graph from the bottom left and leaves the graph from the top right, which we've denoted here with these arrows with the dots in between. That's the end behavior of a graph. So keep a hold of that. We're going to come back to it later when we start drawing pictures of polynomials in general. So another quick example. We've dealt with zeros of functions before, and now we're going to deal with functions of a very particular sort, that is polynomial functions. But the zeros part of this is really no different. The definition stays the same. So in this example, we're looking to find the zeros with their multiplicities, which is a new thing here for us, of the following two functions. In part A, the function f of x, which is 7 times the quantity x minus 3 quantity cubed, times the quantity x plus 4. And in part B, g of x is minus quantity x minus 6 quantity squared, all multiplied by the quantity x plus 3 quantity cubed. So we'll go ahead and go through part A together, and then you can work on part B. So anytime you're looking for the zero of a function, it doesn't matter what kind of function it is, zeros are x values at which y is 0. So you'll notice that we've set y, that is f of x, equal to 0 here. But f of x in this case is 7 times quantity x minus 3 cubed times quantity x plus 4. So we've taken that and set it equal to 0. Now, by the zero factor property, what that means is that one of those factors is 0. Either x minus 3 equals 0, in which case x equals 3, or x plus 4 equals 0, in which case x equals minus 4. These are the two zeros of this function, and this is all old hat stuff that we've covered before. The new thing is the multiplicity. So the multiplicity of the 0, x equals 3, is also 3. The 3 is coming from the exponent that corresponds to that linear term x minus 3. So x minus 3 shows up to the third power. That third power is the multiplicity of the 0, x equals 3. And in a similar way, the multiplicity of the 0, x equals negative 4 is 1. Notice that there's a hidden exponent of 1 on x plus 4, all quantity to the first power. Nobody ever writes the 1, but it's there. And for that reason, negative 4 has multiplicity 1. So go ahead and take a shot at part B, pause the video, and come on back when you're done. So now that you've taken a shot at part B, we can go through the solution here. So again, anytime you're looking for the zeros of a function, you set y equal to 0 and solve for x. In this particular case, again applying the zero factor property, either x minus 6 equals 0, in which case x equals 6, or possibly x plus 3 equals 0, in which case x equals minus 3. Again, the new thing here is the multiplicities. The 0 x equals 6 has multiplicity 2, and the 0 x equals negative 3 has multiplicity 3. And again, these correspond to the exponent on the corresponding linear factor. And really that's all that's new as far as the polynomial section 4.1 is concerned.